Mega Mechatronics.
Welcome back to the Mega Mechatronics Bootcamp series for mechanical engineering. We're covering topics in materials. We'll be looking at failure analysis. And these tutorials are not a be-all, end-all, and I am just touching on the surface. In any of these subjects, in one specific area, someone can spend years writing a thesis on just one little thing, or even a lifetime of trying to figure it out. But what we're going to look at is the very top level, and I'm just trying to inspire you and give you that just base knowledge to know when to look deeper and know when you see something to say, hey, I've seen that before, and then I know where to look that up, or I know where to start to begin. So let's get into this. So failure analysis, we're going to be talking about how metals fail. And what we want to do is investigate the failure, just like Sherlock Holmes. We're going to examine and evaluate all evidence because we need to find out that root cause. We need to sort of go back in time through the chain of events because things are not always cut and dry, just like in real life. So the failure mode, that is how it physically fails. What happened? We're not saying how, we're looking at the actual failure of whatever broke. So an example is a fracture. You can easily see this tap just broke off right there. Whether it was over torqued, it got stuck, someone was abusing it, someone was bending on it while they were turning it. So fracture, that's very common, and these other things typically lead to a fracture. There's distortion failures. So it doesn't have to fracture. It can just bend out of the way, and that's a failure. You see the sign here that's not acceptable. That's a failure, even though it didn't fracture. Wear can cause lots of problems and lead to catastrophic failures or even fractures. So this is an engine, a bearing that was probably it's from an engine. When those, like a rod bearing blows out, then you start heating up your crankshaft and you can even break your crankshaft from the excessive heat, and that's ruining your, heat treat and fatigue protection. And then you overstress it and it breaks. So wear can lead to failures and inefficiencies and catastrophic failures as well. And corrosion. Corrosion can definitely lead to excessive wear, distortions, and most likely fracture. So how can we visualize stresses? And I'm bringing this up because we need to learn where to expect a failure in a part. So if we understand the stresses a little bit more and stress concentrators, things like that, we can get a better idea of what was expected. So for example, let's take a look at this picture. And it might look confusing at first, and I don't blame you. What this is the section of a part, so physically how that part looks, plus a graph that's integrated into that, a physical layout of the graph within the physical layout. So the graph actually corresponds to the physical shape of that part. So you can see there's a C, a 0, and a T, and that's representing a compressive stress and negative stress. And then going to the right is a tensile stress. And then for our other scale of this graph, we have the depth. So you see the top edge of the part is actually that top edge. That there's a line in the middle. That's actually the middle of the part. And then going to the bottom side. So if we analyze this graph, what you're looking at on the top side is a tensile stress. And since that line is on an angle, that shade, it's crosshatched, you can see the maximum tensile stress that this part is seeing happens to be at the very surface of the part. And then we move into the middle, and you see there's no stresses there. You can almost think of that as like the pivot point. And this is a very symmetrical example as well. But we're just trying to get the idea across. So we have our tensile up there. And then we're moving to the bottom side. And what you're seeing, obviously, at the very bottom edge is the maximum compressive stress. Just happens to be at the very surface. And that's typically how parts react to stresses, where the surfaces are being the max stress. And in our video example, you can again see how I'm bending that piece of paper, and it's going to pull apart at the top because it's under tensile, and then you see it buckling at the bottom because that paper is trying to come together, but it'll buckle up. So moving into stress concentration, let's look at some tension examples. So on the very left, A, is a part being pulled apart, much like just like a tensile stress that we talked about. So you see there is no stress concentration because that line, that crosshatch line, is straight across from edge to the center to the middle. And you see there's a 0 point, it's under tension, and here's the center, and it's equal across the top. So moving to the middle example, we see a couple notches cut into the sides, to the edges, and we see there are stress concentrations here. You see these spikes right at the very edge inside of those notches. And then we have a hole that's drilled through this part. And again, these are under pure tension. These are being pulled apart. And you see there's stress concentrations at the very edges of that hole, those spikes. And now let's look at a torsion. This is where we're twisting this rod or this part right here. So again, on the left, we see there's no stress concentrations. And because we are twisting it, you see there's no stress in the middle because again, that's almost like a pivot point. And then the max stress is on the very surface, and that's just how materials react under a torsion. But then on the right, we have a hole that's drilled through. So you see that the phantom line there showing a hole that's drilled through. And again, this part's being twisted. It's under torsion. And you see there's stress concentrators under tension side on the very edge, outer edge, where the drilled hole is. And going back to our bending example, there's something a little different here. Because remember, with this bending example, we're having both tension and compression. And you see how those notches in the part create the tension and spikes in tension on the top side, and there's a big spike in compression on the bottom side. And again, this is pure bending. And here's like a press fit example in a static. It's not being bent or anything. This part, there's a rod being press fit into a tube. So you see the tube's inside surface is under tension right at that inside surface. And that makes sense because that rod is trying to stretch that tube. And then to balance that out, the rod is under compression stress because that tube is trying to squeeze that rod together. And the max stress on the rod is at the very surface under compression. So some more examples. Here's our Sharpie test. And remember that notch? That's put there on purpose so that gives the scientists and engineers a consistent place where that part is going to fail. And that leads to more consistent test results. And let's look at the shear pin on like a snow blower, where you can control how the part fails and the failure mode. So you know if something gets jammed in there at a certain force, this pin will break, and it'll break at these points and give us a predictable and most likely safe way of breaking. And over here we have corrosion pitting. And this is creates stress concentrators. You see at a microscopic level, and a couple pits here have some very deep and sharp points of stress concentrations. But all of these are examples of a stress concentration. And looking at another example of pitting, we see like a shaft here with corrosion and then these pits. And if we zoom in, you can see there's the pit at the top, and then that led to a crack that started at the bottom of the pit, because those pits are acting like stress concentrations. Again, going back to this pure bending. So you see that notch is synonymous with that pit. So it's creating a stress concentration there of excessive stress. And even threads. You can see threads are filled with stress concentrations, because a bolt's going to fail at the root or the bottom of the thread. That's where likely your failures are going to come from. So the location of the failure is very important. Expected versus unexpected. Take a sip of some coffee here. So let's say we have a fixed structure with a bar that's attached to it, and we apply load to this. At this point, where it attaches to the fixed structure, that's where we would expect it to fail, because that's where the max stress theoretically should be on a type of load like this with a bar. However, if let's say that the bar fails at this point, that's unexpected. We didn't expect it to fail there. We expected it to fail at 1. So what this is a red flag for you to just look a little deeper. Was it corrosion? Was there damage there? Was there a scratch, a gouge? What happened? Why did it fail right there? Did the paint chip off and cause corrosion and pitting and these things? So that's something to consider, and why I was touching on those stress concentrations and diagrams of how parts are stressed, because you want you should have that knowledge of where things are expected to fail versus unexpected. So let's get back into ductile and brittle fractures. And this can be easily done by visually inspecting the part. So again, we have deformation, where the parts moved, and then even brittle failures. And those are indicators of possibly you're using the wrong material, or something's wrong, or maybe you need to make some changes. Maybe the bolt you're using is strong, but it's too brittle, and it's breaking and falling apart, where you could put in maybe a softer bolt that would bend instead of completely failing. So, touching on the brittle fractures a little deeper, let's say you had a bunch of time on your hands, and someone said, hey, can you put this pan of peanut brittle back together? You can do it, because this peanut brittle is extremely hard and very brittle, and you can actually put the peanut brittle back together like a puzzle, because those little nodules on these puzzle pieces are intact and will fit back together. And then looking at like a brittle metal, you can see that there's thousands of these little nodules that stick out, but they are stable, and the pieces can go back together, and these crystals will line up again. So, to sort of make that a little more clear, let's look at an application of a brittle fracture, and how we can use that brittle fracture to our advantage is with automotive rod end caps. And these even come from the factory, high performance. these are cracked cap rods. So they'll build this rod end, and they'll put it in a special fixture, and just crack it off. So the advantage is a very stable mating surface. So when you put these back together, and when the engine's on their load and it's vibrating and things like that, these caps are going to be perfectly aligned, and nothing's going to change that. If you torque it down to the right spec, it's going to be very stable. And here's some examples of distortion failures. Old hotel beds, the bed springs are distorted. They lost their load. They lost their height. They are being bent down more easily, and they're sagging. And then here's a sagging leaf spring on a vehicle that used to have a nice curve in it, and now it's sagging, and the car is sitting funny. And even a measuring tape has this unique concave shape to that tape. So you can extend the tape out several feet. However, if you distort that concave shape, it'll fail. It'll bend over and bend down, and that, we can consider that a failure. Just because it got a little distorted, it failed. And here's an example of a bicycle. The bicycle technically didn't break, but it did fail because it bent and changed all the geometry, and will probably eventually lead to a fracture failure. Let's look at some bad residual stresses. We are going to talk about residual stresses up here, but here's an example right now. Stress cracking. So these two tubes were welded together, and they used the wrong manufacturing methods, or didn't complete the manufacturing methods, which led to a tensile force between these two different parts that are, after they welded and cooled it down, they're pulling apart. So having that residual stress in there, and you can imagine a tiniest corrosion pit gets generated right at the that fusion line, that area, and then it just gets worse from there and cracks, where a part that was properly manufactured could be filled with corrosion, and because it doesn't have these residual stresses in there, could maintain its structure. All right, let's get into fatigue. So fatigue is typically a cyclic stress on that part. So it's being constantly stressed back and forth. So looking at this chart, you see two scales here, a stress scale on the vertical side versus time. And it's almost looking like almost looks like you're looking at a sine wave, like the power coming into your house or electronics, but this is actually a stress. So in this particular example, very nice, even stress, and you see it's being stressed on the tension side. So the space between the zero and the minimum of those valleys is a pre-tension, because it's not reaching zero, or it's not going into compression. So here it's just being stressed more and then stressed a little less on the tension side. And here's probably more real world stress, when things are out of whack and it's not perfect and it's going into negative stress and the compression and moving around. And things like this are curveballs, you can say, where some parts may enter a certain harmonic frequency, a natural frequency, and that the stress being applied to that part matches that natural frequency, and then things get really excited. Things get out of control beyond what the engineers have expected, or it just could be the nature of how that part is stressed. So some examples. Parts and objects cycled under stress. We have a trampoline. And these springs, well, we can see there's little air between those coils, so we can say it's under a pretension. And then every time you jump on it, it's going to increase the stress in those coils. And if you put more people on it, or adults, for say, they're going to reach a higher peak stress, but they are going to be cycled every time you jump on it. And the bow and arrow. So the bow is going to experience a cyclic stress. So every time you draw the bow, it's going to increase the stress. And then when you release the arrow, it's going to see an odd stress pattern and things like that. So bows, especially a wood bow, is not going to last forever because it's being cycled. And here's another fun example. The next time you're flying on a passenger jet and you have a window seat and you can see the wing, right before takeoff, reference that tip of the wing. Just stare at it, reference the tip of the wing, and as you accelerate up to speed, you'll see that wingtip just lift. And it's amazing and kind of unexpected or a little bit scary. But that's how the airplane was designed. And it's designed to handle these cyclic stresses. So don't be worried about it. There's very rare for an airplane wing to fail like that. But we don't want to forget there's thermal, mechanical stresses, because materials will expand and contract depending on the temperature. So here is a cast iron exhaust manifold on a car, and you see it develop a crack right here from just being every time, thousands and thousands of times that this vehicle was cooled down and heated up and cooled down, and that eventually led to a fracture. So let's look at the stages, the official stages of fatigue failures. Stage 1, we have the initiation. This is where it all begins, and likely at a stress concentrator, but this is where the part starts fracturing. And then stage 2 is the propagation, where that fracture, every time it gets loaded, it starts growing and growing in the very tiny microns, very, very small amount. But depending on the material and the size of the load, it could take 3 cycles or it could take 50,000 cycles. But every time you're loading that crack's getting bigger and bigger, and that's the propagation stage. And then the spectacular ending would be the rupture, when we get our catastrophic like failure, complete failure, where the part breaks or bends or collapses. So looking at an example, we have a fatigue fracture with visible beach marks. There are beach marks that are typically visible to the eye, and you could see how those beach marks radiate from the origin. So that's a very good indicator. And this is the ideal. In the real world, you don't always get so lucky to find these beach marks or have access to an electron microscope to view the striations, which are similar to beach marks, but appear in different materials and different sizes. So the striations are going to be much smaller. And then you see that sort of gray sandy area, and that's the rupture area. So we have our initiation at the origin. We have our propagation through these beach marks. So starting from the origin, it's getting bigger and bigger and bigger until we reach the rupture stage, where the part completely fails. So let's look at a picture here, and we can almost see, if we follow the beach marks that we could visibly see in this picture, and we follow those beach marks, we can almost get a good idea where that origin was. Around here. And then we're propagating over time. And you could tell it was over time because there's rust. Look at that rust, that oxidized orange, dark brown surface. So you can almost tell that this has been propagating for a while. And then it gets lighter and lighter until we rupture down here, where we see sort of a brittle fracture. And we can make out how far those beach marks made it to that final point. So it almost went through three quarters of this shaft before it finally failed. And here's a close-up of striations on a failed part, and you see, oh, it's absolutely beautiful. This clamshell look, and you see how it perfectly radiates. There's that little white arrow at the bottom, at the initiation point, at the point of origin, and you see how those striations just radiate out from there. So let's look at this example again. We have a torsion bar. It's under a torsion load, a torque load. And let's say this part is 10 millimeters in diameter. Let's put this into a graph form, just in case you're confused about the physical layout and the part being in the picture. So I'm going to draw the same exact graph over here. So we have our compressive, 0 point, and tensile stress scales on the side. We have the depth. Now look at this depth. We have 10 millimeters here. And you can see on the vertical lines on each side, that's a 0 point, because those are the edges of the part. And as we move towards the center of the part, the depth goes to 5, and then it starts back to 4, because it's only 4 millimeters deep from the other line. So here's the center of the part, this 10 millimeter diameter part, and here's the center point at the 5. And then drawing the stress data, we could see it's on the tensile side. And here, at the very edge, at 0 depth on the surface, is the point of maximum stress. Now this is sort of precursor to looking at this case study of beneficial residual stresses to prevent failure, whether it's a distortion failure, what we're going to look at, or a fatigue failure. So let's do a case study on the gull-wing door assist torsion bar for a DeLorean, the Back to the Future car. There's actually torsion spring bars that assist the opening of the door. So looking from the front, the doors are fully open. But let's say one of the cars got through the factory, and after they closed the door and then opened it for the second time, they found that the door on the passenger side was sagging for some reason. And that of course is that's a failure in quality. Definitely failure. So let's look at what happened here. So we have our passenger door torsion bar, and we have our driver door torsion bar. And let's say the dashed orange line is the material limit. That's whatever material they're using, that's the yield strength, for example, before it's the torsion bar starts permanently getting deformed and failing. So let's say the scientists or the quality engineers found out that there was no residual stress on the passenger door torsion bar. And on the driver's side, where it didn't fail, they found compressive residual stresses at the surface. So both of these parts are unloaded at this point. They pulled them out of the vehicle and they're just sitting there on the table. So you can see on the driver's side door, at the surface of the part, there is a compressive stress. And then as you go deeper, it'll transition into a tension stress because these stresses have to balance out within that material. But you see there's a compressive residual stress at the surface of this torsion bar. So what happened? Why did it fail and why was that sagging? Well, when they closed the door for the first time, the material stressed beyond the stress surpassed the material limit, the limits of that material, and caused a plastic deformation, which changed how that torsion bar works, and it actually loses its strength. So why did the driver door survive? Well, when they closed the door and you see those little spider legs, you could see how on the very edge where that compressive residual stress was, how it compensated for that and how it prevented it from, at the surface, exceeding the material limits. Look at that. So going back and forth, you could see how that compressive residual stress reduces the maximum tensile stress on the surface of the part for the same exact load. So this concept here is what makes valve springs so durable, and makes them last so long. Crankshafts and any parts that are cyclically loaded. Aircraft, this is a very big deal. These compressive residual stresses within airplane parts. Very important. So again, the max stress is below the limit. So preventing failures, failure mode and effects analysis. Well, you need to look at your part and for fractures. So why did it fracture? Well, probably because it was fatigued, it was overstressed, there was corrosion. So things you can change for distortion failure is prevent that distortion, prevent something from hitting it, prevent a car from running into it, increase the structural rigidity of that system. Wear. Do you need to improve the lubrication systems? Did you forget to lubricate it? Does it need a different type of material that are mating with each other? Does it need more surface area? Things like that. And corrosion. What happened there? Was there galvanic corrosion? Were there dissimilar metals? Did the paint chip off? Did you not paint it? What type of environment? Was it designed for fresh water but was brought to salt water? And things like that. So you need to find that root cause. Why did it fail? Why did it wear? It broke, but it broke because of this and this. And going down the line, it started pitting. The material was defective. And that's how you can improve your systems, by analyzing these failures and even analyzing it before you produce it. You want to understand the failure modes. How could this part that I designed possibly fail? And what are the effects if it fails? If this part bends, will that be a safety concern? If this part breaks, what's going to happen? Will the operator be injured? So you need to think of those before or as you're designing it, so you could sort of foresee the effects of that failure. Well, that's the end of this one. Thank you for watching.